Hi, so I wanted to do an overview video on everything I did in my first computer architecture class, CPRE 381 at Iowa University. During this class, for the lab portion, we would use VHDL to design multiple MIPS processors, starting with a single cycle processor, and then designing two 5-stage pipeline processors with a software and hardware implementation. For the software implementation, we use no-op instructions to handle the data and control hazards, and then the hardware implementation had a hardware implementation to control the pipeline registers, and then also handle forwarding and flushing. So I wanted to overview all of these and also the extra credit project we did, which was a FPGA wrapper to get our hardware scheduled pipeline onto a DE2 115 Altera FPGA development board, digital logic class that I taught previously. So to begin, I'd kind of like to overview single cycle pipeline and kind of how we went about it, designing different modules, their purpose, and kind of what we did for the class and why what we did was effective. So up on the screen right now is the overall schematic for the single cycle MIPS ISA processor. To overview the instructions that we had to do, I have this control sheet here with the list of 33 instructions on the left. Alt is a pseudo instruction used mostly just for this project to indicate when the program would be complete, so it is the last instruction we have in programs. So the first third of the class was spent learning about MIPS ISA and how to decode instructions, how to convert basic C programs such as a Fibonacci sequence, bubble sort, for loops, and so on, assembly instructions. Then in the second portion of implementing how to put these into an actual processor and decode them and carry through with these instructions and get something. So you can see a mix of these instructions here. We have multiple R-type, I-type, and J-type instructions from the MIPS ISA, including add, subtract, and load up or immediate. So some pretty basic ALU operations. We also have some memory operations with the load word and store word, which will be handled data memory module. And then we also have some conditional and unconditional branching. The conditional branches include BEQ, branch equals, and BNE, not equal, and then some other ones like BGTZ, BGE, where they will branch if it's 0 or less than equal to 0, and so on. So that's kind of a set of the instructions. So we had this spreadsheet to determine what each of our control signals should be decoded in one other module. Pull this back up here. So I'll kind of walk through each of these here. So the fetch module is in charge of updating the program counter, which, unless there are any jumps or branches, it will increment byte addressable, so it'll be PC plus 4 for every following instruction. But if there is a conditional or unconditional branch, then the control flow can change, so then the PC might need updated branch address, and then it would always need. We have a multiplexer before the instruction memory. So the fetch module outputs the program counter, which is then acted as a 32-bit address, which is truncated to 10 bits for our processor so that we have a fast simulation. It doesn't crash with 2 to the 32 possible addresses because we do not have a program that long. We also have a multiplexer to load in our own instruction memory, which is useful to write to the instruction memory at the start of our simulation testing. The instruction memory and data memory modules were provided to us for the class, but we ended up modifying those for the A route. And then we have the control module up here on the top in purple. So the control module takes the input of the upper 6 bits of the instruction, 32 bits, which is the opcode. And then it also takes in 6 bits of the function, which is the 6 lowest bits. And the function field is there for the R-type instructions. For R-type instructions, the opcode is 0. So then we have to function those. And then we take the RT address in because if the opcode is 1, we have to differentiate the RT address for some of the special branch instructions, including, this set of them down here. So yeah, and then we also have a register file. So there are 2 read ports and 1 write port. The RT and the RS addresses are our read ports as specified by the MIPS ISA. We are required to do that. And then we also have the write port, which can be flexed. And then we also have a write enable bit rolled here with this. And then we also have a 16-bit sign extender. So we have a control bit so that it can be sign extended by 0 or it can be extended with 0 or extended by the sign of the most significant bit of 16-bit immediate. This sign extension is used since the MIPS ISA receives a 16-bit immediate value, but then it does the do operation 32 bits, which you can see here by the multiplexed input going into second ALU. And then there's also, from this control module, it also takes some controls that sends to the fetch module, one to the sign extender module, one for the register write control, one for the data memory write control, and then 10 bits to the ALU control, which acts as a lot of select line switches between the different submodules for the add sub operations, the logic operation, shift operation. And then, for example, one control bit could be to choose that it's going to output one of the shift outputs, but then either shift left or shift right. So we need another control to dictate what the shift operation shift submodule. We also have overflow detection, where one control bit is output to check from the control module, and then overflow indication is indicated from the ALU if overflow occurs for some. And so there's a difference in that between the unsigned, like add and then add u for the unsigned version, so that dictates that. shal is just driven directly from the control module after it is decoded from control, since it has its own unit. And then the contents that are written back to the register file are multiplexed between ALU output, the data memory output, or PC plus 4. That is due to the jump in link instruction, since it has to write the PC plus 4 after a jump in link a specific register, so that when you do jump return or JR, then you can go back up to it. So that's for calling procedures. Assembly program, kind of like a function. So these reports were all ones we were required to fill out. This one's pretty lengthy with 31 pages. The second report is 23, and this is our software and hardware pipeline. Third one is performance analysis comparing the three. Extra credit, this is just something. So I'm not going to go through everything. There's a lot more details on like testing and stuff, but I figured I would do some of the code for the single cycle and then maybe come back to the schematic for pipeline ones and just kind of talk about it. Like I said, there's a lot of stuff here, so I can't get to everything, but I just kind of want to talk about what I learned from it, what I took away from it, why I enjoyed the class so much. So looking back at the single cycle, I kind of have to appreciate how simple it is. After doing the hardware pipeline and handling stalling, forwarding, and flushing with hardware instead of no ops with the software, it's very nice. And so I had one partner, Thomas, who I've worked with a lot in Solar Car and other classes. So he was very helpful in this. And then, so what he did is he worked on all the submodules for the ALU. So it was my job to test those. And then I designed the control module and the fetch module, which would be update the program counter, while he tested those. So to hop into those, this is actually my first time using HDL. I made a video over Christmas break going over working with the first FPGA development board, Fastest 3, talking about how I went about that process, what I learned from it. And so it was really nice to learn VHDL and kind of compare both of them. So like I mentioned, the three inputs are the opcode, function, and RT address. And then we just output a mix of tons of control signals that go to the ALU, the data memory, the register file, fetch module. So like I said, we tried to comment our code and make it very clear what we were doing if you didn't have the 30-page design sheet with it. We used a process statement, which in hindsight, we probably just could have used a with select statement. We just do the same thing here with a case statement, where first we read the opcode. If it's all zeros, then it indicates it's an R-type instruction. So then we use the function to determine if it's an instruction like an add u, and, nor, and so on. Otherwise, it just defaults all to zeros. We need this when others to cover all the cases that aren't covered when this function is these set of bits. Otherwise, we would get error when simulating and synthesizing. When the opcode is 1 in decimal, then we have these special branch instructions, which is a special case why we need RT address, like I mentioned before. Otherwise, we can just read the opcode as is for some of the I-type instructions like add IU, load upper immediate, load word, store word, some of our branch stuff, and halt. Then pretty much after that, we just decode this entire bit vector that's 23 bits long, and we split it up into the controls that we had mapped out at the top. And so it was Thomas's job to test this. So pretty much he just did every possible combination and a few that were wrong to verify that we would get the right controls for everything. For the fetch module that we designed, I can actually pull up a schematic. Let's see. This is my schematic. It is pretty messy. The general idea here was just to get an idea of it and then implement it and start testing it right away. So right here, you can see we have our program counter register. It's an asynchronous reset, synchronous write with a write enable. And so you can see here we have an adder to calculate the PC+4 address. We also have a few different multiplexers. We have an adder to calculate the branch address, which adds PC+4 plus a extended immediate. And then we also have, that's PC branch. So then the indicator, because you won't always be branching because it's a conditional jump, we have to compare if we're checking for a branch, which is from our control module, and the determination of if a branch actually should occur from our ALU output. And so those are ANDed together for the select line here. And then that will go to the PC select, which actually controls if you're doing PC+4, possibly a branch, a jump, or RS data. And then that gets written into the program counter registered data, and then will be written upon the positive edge of the next clock cycle. So again, it was my partner Thomas's job to test that. And then we can go into some of the tests as an example. Let's just go to the ALU. So we made custom do files that were loaded into ModelSim. And so what this would do is this would delete the work folder, recompile everything in our source files, and then start the simulation. We actually added, we had commands to add in the waveforms we were looking for, and we color coded them and added dividers. So it was really easy to rerun the test if we wanted to add more unit tests or verify that something worked after a bug fix or so on. To go into like to find the actual test bench. It has been a bit since I've been in here. So we have, here we go. So we also designed the test benches in VHDL. So you'll see this one's really long, like about 1,000 lines. But so we didn't have to check these by hand. We actually had a couple sets to automate that. And so you can see that with these process statements here, where we have P branch check, P overflow check, and so on. So basically, we take the calculated expected value and we compare it with the outputted value. And then if they differ, then we raise that error flag so that you can easily see when the signal changes from a 0 to 1 at any point in the test bench. And then if you go into here, you can see an example of that. So let's see. Let's just take this as an example. So this is the shift submodule. So I also tested all the submodules for the ALU, but you can see this S result error. So if this is an error for any of these test cases, it'll be raised to 1. Otherwise, it'll stay low and it'll check everything as we go. So we can just focus on creating these test cases, which we did create them manually. It would have been nice if we could randomize it and just kind of have it run against a seed. We didn't do that, but this was a step up. We have the color-coded waveforms and the dividers, and it was very helpful. And then we'll move on to wiring everything up. Like I said, I kind of want to keep moving because there's a lot to talk about. um, but we can talk about the top level file. So again, pretty much what we did is after designing this schematic, we worked on wiring everything up in this MIPS processor folder. And also one other thing, we designed the register file and the 32-bit extender beforehand in a previous lab, so I'm not going to cover those. They're pretty straightforward about what you'd expect to. Let's keep moving. But the big thing here was just keeping track of all the signals. And so what we did is any internal signal, we had the prefix S underscore. Any input, we had I underscore. Any output, we had O underscore. This was a provided module that linked up into tool flow for the course so that we could get a grade on it. So we didn't have full control over that, but what we did design and implement, we tried to keep with this consistency, and I think that just got better throughout each of the processors in the projects. So you can see here with VHDL, one thing with VHDL is it's very verbose and wordy compared to Verilog, and it's nice in a way because I feel like it helps catch some errors sometimes, but man, this was a long file for the 5-stage pipelines. This one wasn't too bad looking back on it. But so, I mean, pretty much, you're just wiring everything up. We already unit tested everything together. So the only issues we had here was, I think, naming a signal wrong or maybe having it the wrong amount of bits. But, you can see here we have our internal signals for our decoded instruction, and then we feed those into our control module, our prefetch module, and our register file. And just kind of keeps on going. But then there was a automated tool flow where we could run all of our assembly programs that we designed, given Fibonacci sequence or what we designed for bubble sort, and we could verify that they worked with every cycle. And that was an automated process that was provided to us. And so if you're more interested in some of those or the write-ups on each module, I have included the reports, but otherwise I will get into project part 2. So next, we were ready to implement the 5-stage pipeline. And so for this, we had to include 5 stages. So I will pull up the high-level schematic. So this is the schematic. I know you can't read every single little signal, but you get the general flow. So this is the schematic for our software 5-stage pipeline. Our pipeline stages from left to right follow the instruction fetch, IF, instruction decode, ID, execute, EX, data memory, DMEM, write back, WB. So the intent here with the 5-stage process is to decrease the critical path. So in our single cycle processor, we noticed a maximal clock frequency around 20 to 25 megahertz, if I'm not mistaken, which was pretty slow compared to what we ended up getting for the pipeline processors, where we got around 52 megahertz for the software pipeline. And so this is done by breaking up the components and making them a similar latency between the stages so that we can have a faster processor and a faster clock frequency. And so ideally, the cycles per instruction is still 1 minus the fill time to get the first instruction from the IF stage to the write back stage, but ideally it should be 1. Now, with data hazards and control hazards, that's not the case for the hardware pipeline. But for the software pipeline, we just introduced no-op instructions, which would prevent the data hazards from happening because there would not be any read after write dependencies or any control flow issues because there'd be enough no-ops in between to determine that. And so to do that, we modified our own assembly programs and manually inserted those no-ops in based on how we updated our. So we designed these pipeline registers, which were between the IFID stages, IDEX, EX, DMEM, and write back. And so you can see here in the IF stage, we have the fetch module and the instruction memory module. These stayed relatively the same for the software pipeline. Eventually, we add stalling in the hardware one. For the ID stage, we decided to move the branch module here. And so what this did is it reduced the number of no-ops because it previously was determined in the ALU stage, or the EX stage in the ALU. So they would require 2 no-ops to prevent control hazard. Because if you didn't have that no-op, then you would be pushing instructions through the pipeline when you didn't know if you were taking a branch or not, and you might have to wipe them away, but we did not implement flushing at the time. So by moving it one stage earlier, while it might affect our maximum latency critical path by a little bit, it would reduce the number of no-ops from 2 to 1 for branch instructions. And since we decoded the jump instructions in this stage, it made it consistent of having unconditional and conditional jumps and branches to have one no-op each. And so that helped reduce the number of instructions, which had a improved execution time. So we saw with the software pipeline in general that the maximum clock frequency went up a bunch. The CPI stayed at about 1, very close to 1, minus that fill time. And then our number of instructions was way larger because when there was read after write dependencies and data hazards, there would be, 2 or 3 no-ops needed. And then for branches, it could be up to 2, or we pulled it down to 1. We also reduced the number of maximum potential data hazard no-ops from 3 down to 2 by updating our register file. So if there was a dependency between the decoded ID stage and the writeback stage, the contents that were being written into the register file would not be written until the positive edge of the clock. And so if there was an instruction trying to decode that in the register file, it wouldn't be able to get the content. You have to have another no-op. Or you could multiplex the output if there was a dependency, so that it would pull in the data that would be written in on the next cycle, but you could forward it sneakily in the register file. So that helped reduce our maximum data hazard no-ops down to 2. And so both of these things reduced the number of instructions and helped for improved performance compared to our single cycle processor. And so we have all of these processor designs in the same GitHub folder that you can see on this video or on my website, but we can go in and just take a look at it too. And it was really nice being able to reuse a lot of this code and just improve the performance of it, and kind of take what we did before and take it to another level. So for example, for the register file, where did we box this? Let's see. I will not get into this right now because it will take me a bit. But you can see that the register file has changed, and we can reduce the number of maximum no-ops. And then we have also the branch module, which we basically just ripped out of the ALU and instantiated it as its own piece inside of the ID stage, which helped reduce the maximum no-ops from 2 down to always being 1 no-op. And that's nice because we always had to have 1 no-op at this point. But we just pulled that out of the ALU from before, as seen. And there wasn't much else with the software pipeline. I mean, we can talk about the performance comparison. So I'll get into this with the hardware one a little more, but just looking at the first 2 main tabs, you can see the number of instructions for Grendel, which was kind of our end-all be-all benchmark. It had pretty much double the number of instructions. And so you can see that the CPI is very close to 1, like we talked about. But yes, the total number of cycles is about double, but the maximum cycle time is over double what it was for the single cycle processor. So you'll see that the execution time goes down from 85 microseconds down to 82. And so it isn't a huge increase, but we also didn't change a lot. And I think a lot of people in the class could have seen that it might have actually been worse than the single cycle if they didn't update and move the branch to the ID stage or the read after write dependencies between ID and back stage. But seeing this was really interesting, and it made me really, really want to put this on an FPGA to see it actually run. But we also still have the hardware one, so getting ahead of myself. But again, a big challenge of this was we made our own do files. We still did unit tests for all the new modules we designed and the part. we created the do file so that we added waveforms based on what stage of the pipeline they were in. And we also appended a prefix of what stage that internal signal was in. So you'll see that the instruction decode signals are all S underscore ID underscore, instruction, opcode, function. You get the gist. But, again, if you want to see more of this, this is in our Project 2 report for the software pipeline. And we also have some waveforms for our bubble sort. We also have a proof that the no-ops are being inserted. There's a lot here. Honestly, I've already been talking for 25 minutes. I'm just going to still be going. But if you want to see more, we tried to be very detailed and thorough in defense of our design, because I think we also got a lot more out of it. One thing I do want to show, though, is all of these controls. So you'll see we have a ton of tables down here. So the controls got way more interesting after designing. I can't see very well. Some of these are a little cut off, but you also can download this. This is on my website too, so on GitHub if you're interested. So we have some tables showing the data hazard dependencies and the forwarding dependencies. This looks like a hard one. Oh no, software one. Oh, I got these mixed up. So how this works is we have, the control operations, which kind of explain all the controls from the first part. Oh no, these are all broken. That's sad. They worked in Google Drive, but normally what we did is we had pretty much which signals would propagate between each stage, between the IF, ID, EX, EMEM, and writeback stage, so that you could see that when they were created, if they would propagate. And then we also had a little thing in here that would concatenate the text, and you could just pull these signal names straight into VS Code, get them into the VHDL stuff. But if you want to see the actual names for these screenshots are in our report. And we should have, okay, so our hardware pipeline, which was our last processor, is right here. So you can see there's a lot more multiplexers, and there's a couple modules that go between stages. So the big one is the hazard detection module that's in yellow up here. And this is what we started with doing. And so pretty much this just detects if there's going to be control hazards, anytime there's a branch or jump instruction, and then when there are data hazards. So basically when there's after dependency occurring. And so what this would do is it would take the input of the register write control signal and the register write address from the write back in the DMEM stage and compare it with those that are getting decoded in the ID stage. Go into our code for the hardware process. Hazard detection. It's a very similar flow to what I covered before with controls getting decoded, where it does, again, take the opcode and the function to check. And so, pretty much what it does is it decodes what the instruction is, and then it determines if it should stall or flush or do nothing and let forwarding take over. So we initially developed this without any forwarding in mind, and so we implemented stalling with hardware checking for all of our arithmetic instructions, load word, store word to generate an address, and so on. And then for the controls, we also would, just stall right away. And then we implemented flushing for the controls, where basically for the conditional branches, if there is a branch in the ID stage and then we take a branch, what is getting buffered in from the instruction fetch stage is going to be PC plus 4, but now we don't need PC plus 4. So we have to flush away this IFID register by writing zeros to it and update the program counter so that it fetches the correct value on the next positive edge clock cycle. So then we worked on forwarding, and there are 3 different forwarding cases as seen by the multiplexer in the stage. So we have forwarding for both of the ALU inputs, which can come from either the register file or also the register file or it, like an ALU input. And we also have forwarding for the data memory. And so that's the data memory data. So the address for the data memory module in the deep stage is actually generated by the ALU. We also can forward. And so the benefit of the forwarding that we saw was instead of stalling and taking more cycles for one instruction, effectively increasing our CPI, we were taking less cycles by pushing this data that was ahead in the pipeline, pushing it to the ALU in the EX stage before it was getting written back to the register file and after those instructions were. So this reduced our CPI, and we still had while a little bit slower, still faster maximum clock cycle frequency compared to our single cycle processor, and a lower amount of instructions since we weren't using no ops. And so then in the performance analysis, you can see here, the number of instructions is the same as the single cycle because we didn't insert all those no ops. The total cycles is larger, and it's a larger CPI, again, due to requiring some stalling and not being able to fix all the forwarding because we still have to stall sometimes in the ID stage. And again, the max cycle time went from 55 to 48. But when you do the math, it's the lowest amount of instructions, or at least the same as single cycle. Yes, it is, right in the middle, like 1,000 more cycles in the single cycle. Yes, the CPI is more, but the maximum cycle time is literally double what the single cycle is. So you get an execution time that's 20 microseconds less than the single cycle and 17 microseconds less than the software pipeline. And so this was really satisfying to see this improvement. And there are a couple more things we could do. We could implement forwarding for a few more locations, and we could have a better branch prediction module. Right now we just had it predict the branch was not taken, so it wouldn't flush away the branch statements if it was not taking the branch. Then we could just use what was fetched in the IF stage, reduce it a little bit. It also depends on the program if you're for your conditional branches, if you're taking the branch or not taking the branch more. Because if you have a really long for loop, you're probably going to take the branch. Like if you have a for loop that runs 1,000 times, you're going to take the branch 1,000 times and not take it once or twice. So it wouldn't be very good there. But and for this performance analysis, this one was really interesting to write up and think about. So what we did was we pretty much just talked about the execution time and comparing what I just talked about. But, if you want to read more about this, it's on my website. It's on GitHub. Go ahead. And so then what we did was we finished with the FPGA extra credit report and synthesizing our board for that. So what we did was we were pretty much done with the project at this point, and we had about a month left and still wanted to learn a little more, apply it to FPGA, see this processor run on real hardware. Because at this point, we were just simulating everything using Model Sim, VHDL, VS Code, so on. So we rented out one of the DE2 115 Altera FPGA development boards. And so what we did is use Quartus Prime, and we put together a bunch of I/O modules, including a debouncer for some noisy buttons, 7-segment display, some clock dividers. We applied that to the DE2 board, and we put our hardware 5-stage pipeline into it. And so the biggest challenge to this was loading the memory. So the memory, pretty much how it worked was in the simulation, we're able to load them through the provided tool flow, but we had to find a way to get this onto the memory directly onto the FPGA. And so what we did is we used what was called a mega function, and we generated an Intel hex file through Mars, which was the MIPS ISA simulator we used for the course and for the rest of the tool flow that was provided to us. We generated an Intel hex file, and then we put these Intel hex files into our Quartus Prime project, and we pointed in our memory files the name of these hex files. So then on reconfiguring the FPGA by loading the bitstream, it would load the initial state of our instruction memory and our data memory. Now the kicker of this was we never wrote over our instruction memory, so that was okay. But the data memory would be written back and forth, written in red, throughout the program. So we had to reconfigure the FPGA to get the data memory set. So that's something I'd like to investigate more in the future, but that gave us some trouble. But we also had some features that I can just pull up the wrapper module. But what we did is we just had this top level module, and I use Verilog for this since it wasn't required for the course, so it was extra credit. I had an easier time just throwing this together in Verilog after what I did previously with work and other stuff. But so we have all our wrapper pins that get mapped to the E2 board. We have a debouncer for a clock button. So we had 3 different clocks so we could multiplex between switches. One was a debounce button, so we could verify different signals on our 7-segment display. One was a 25 megahertz clock, and one was a 5 hertz clock that had a 200 millisecond period, so that it could slowly increment without us having to button all. One issue we found was that the buttons, whenever they were open or not pressed, they would output 1. So we didn't invert our button switches originally, so we were always resetting our processor, and we were like, why are we getting anything out of this? Like, oh, okay. That's one thing with FPGAs, is it wasn't as clear to see as if we did in a waveform, so having a logic analyzer helped for that. So we also had the 2 clock dividers that I mentioned here. We have a select line. We also outputted that to an LED on the board. So pretty much we just had a case statement to pick between the debounce clock, the slow clock, and the fast clock that was divided. We also latched our clock signal based on that halt indicator that was output as the last instruction from our processor. So pretty much when this was asserted, we would latch the signal, and the clock cycle, no matter what it was multiplexed as, the final clock signal would just be latched at 0. That we would stop the program after it was done running. We also had a counter for the clock so that we could count the total number of cycles at the end of the program. This was useful to verify that it was the same number of cycles as our simulation, especially for handling the control flow for the jump and branch instructions, and to make sure that our data memory was updating correctly. Because if our data memory wasn't loaded, we weren't going to branch at the same time. If our branch instructions weren't working for some reason, we were not going to have the same cycle time. So that was really nice to verify. We also had multiple instructions that were ripped out of our processor here, and were pretty much just selected through the 8 7-segment displays on the board for 32-bit values in hexadecimal. So we use 4 bits per value, as is typical with a 7-seg display. So what we did is we had a case statement between the instruction memory, the IMEM output from the instruction fetch stage, which is pretty much just the fetched instruction, the ALU output, the register write address from the execute stage, EX, the data memory output from the DMEM stage, the clock counter, like I mentioned before, and the final multiplexed register write data that would be written to the register file in the write-back stage. And then those are held in the 7-seg output here. And then this 7S seg out reg type is what is fed into the 8 7-seg decoders down here. I mean, you can also see we instantiate our processor. There's a lot more outputs than before. We also set the instruction load, instruction address, and so on to 0, since we were loading those our own way through X files. This was a really interesting project to do, and it was really fun to do something extra. And yeah, we didn't do anything with caching. We did learn about caching in the 3rd portion of the class. I do want to work on interfacing with some different memory modules, and like develop, maybe a L1, L2 cache inside of like an L1 cache in the processor, and then maybe interface with the SPI flash memory on my Bashes 3 board. That's something I've been thinking of. But yeah, that is the project really. We also have a report on, synthesizing all our stuff, just a write up on that. So if you're interested in that, you can go see it. It's also a good reference for us or future students or whoever, because we did submit this for the class. But yeah, I learned a lot in this class. It really opened my eyes up to how things actually work in hardware, and it was a great opportunity to get more work doing RTL work. I really enjoy working with FPGAs. I hope I can keep. So thank you for your time. Thank you for listening. I will see you next time.